Now you have synthesized your design. Okay, so you had written RTL, and your synthesis tool read that RTL and has created a gate and a flop implementation of that. So it has created a gate level information. Now, how do you know that whatever I had written in this RTL and whatever is in the gate level here are equal? How do I tell that? As in, whether the synthesis tool has done its job correctly or not, how do you know? This is verified using something called equivalence checking, and there are equivalence checking tools for that. So what equivalence checking tool does is it verifies whatever has been synthesized by your synthesis tool is equal to what was written on the RTL tool. So there are no, let's say if there are bugs in the tool, it can have created a wrong logic. Okay? Equivalence checking tool, again, it's a static verification tool, or also known as formal verification tool. The equivalence checking, equivalence is checking equal between RTL and gate level netlist. How does it check? Okay, so it breaks the design into flops and checks what is the logic between those flops and check what is the Boolean equation for that logic. So in this, the Boolean equation for this, maybe let's say this is x, this is y. Between x and x is equal to y. Between x and y, if there is a buffer. Now let's say there is a modified version of the design which does this. Here this is x and this is y. Between n x, so x goes here, it goes inverted, then it goes inverted here. Here also the equation is x is equal to y. Since mathematically both of these functions between the flops are same, equivalence tool will say, okay, yeah, this is correct because function is same. Similarly, so it will break the design into multiple parts. So you have this design, it will break the design into flop to flop, input to flop, or flop to output. This part, this part, this part. For each of these parts, it will create a Boolean equation, both RTL level and gate level. It will create a Boolean equation. Let's say this is equation one. This is equation two, and it will verify that these two equations are able to. Okay, so let me come back. So basically, your design is broken down into three kinds of paths. One is input to flops, flop to flop, and flop to output. And let's say this is gate level representation. This is RTL level representation. For each of these portions, it will convert those into Boolean equations, and it will verify those equations are equal. So this equation is equal to this logic, this equation is equal to this logic, and equation are equal. So in this case, you see it when it goes from x to y, this is x, this is y. When it goes to x to y, there is a buffer. So equation is just a buffer, x is equal to y. Here, for the same path, it will check when it goes from x to y, the equation is first inversion and then another inversion, which is same as saying these two nets are equal, so x is equal to y. So it will say, yeah, this logic is same, doing the same functionality, even though it is implemented differently, but it's doing the same functionality. So these are equivalent. So y verification is done. That it's the same logic. Similarly, it will say check here. Okay, let's say this is A, this is B, and this is NAND of A and B. Okay, so A, B, NAND. Here it will check, okay, what is this? Is it the same functionality? It will say, okay, NOT of A and this is NOT of B and AND of that. Is it the same functionality or not? Okay, this is actually OR. Yeah, so OR of A and B. Is it the same functionality or not? If this is the same functionality, which is the case, then we'll say, okay, RTL and gate, even the logic which is written is RTL, the Boolean equation for that, and the logic which is written at the gate level, the Boolean equation for that is same. Now, In order to do that, it breaks it down into three parts, which I said, 1, 2, 3, input to flop, flop to flop, and flop to output, and verifies each of these equations, compare between RTL and gate individually. And if they are doing the same functionality, it says, okay, equivalence checking is clean. If somewhere it fails, it will say, okay, equivalence checking is not good, and point out to you, okay, here it is not matching. Why it is important is because synthesis tool may make mistakes or may have some bugs, then it will be caught here. It is very important in chip design flow to catch these kind of mistakes. So because it's a complex and expensive if you have a design failure at the silicon level. So this is how equivalence checking tool work. And if you see, there are no test bench which is given to it. So it basically verifies it statically or formally, and is a formal verification without giving any test bench. And this is used very widely. Every synthesis tools output is used. It does not only apply to synthesis, it can also apply to other areas. For example, you use place and route tool to modify the design, then also you can check equivalence. So equivalence checking generally applies to a lot of places, but this is the basic concept. It basically converts the design into inputs to flop, flop to flop, flop to output. It creates equation for each of this logic. Once these equations are created, it is verified, okay, this is equal to this is equal to these, and this is equal to this. Each of these equations is verified, and that is how equivalence checking tool works. So we took a simpler example but this in general the logic will be very complex, and that is how it is verified. The tools for equivalence checking, there is synopsis formality, there is from Cadence LEC, which actually verify the synthesis output matches RTL using the equivalence checking concept we talked about, and they do it.